Let's look at this one first. If I have to think a square, and then a square is going to be q lambda q inverse times another q lambda q inverse. That's how you do square, right? And then now you can reassociate this q lambda q inverse q lambda q inverse. What is this q times q inverse? I, right? You don't need to care about the I. That's a square q inverse. That's I. Does not change anything. Okay, a square equals q lambda square q inverse. How about the aq? Do the same operation, equals q lambda square q inverse times q lambda q inverse, and reassociate q inverse q lambda q inverse. That's I again. Then you have the I here. What you have is the q lambda q inverse. You got the idea. We can keep going. Then any a to the m, you only need to raise the power to the middle diagonal matrix. We know it's 1% of calculation if this n is 100, right? So times the q and the q inverse, that's not too much operations either. So we really significantly reduce the computation. We can also extend this to the polynomial. There's no difference if you use the polynomial. Then what you have for the polynomial a, instead of calculating all the m by n element, I only calculate the 1q times the polynomial of the lambda. We now only need to calculate the diagonal element. Everywhere else is 0. And this q inverse. Well, by the way, what we give here is called eigen decomposition. It's a significant skill for computational science. Let's look at an example that we worked before. I think it's in last hour. A is a 3 by 3 matrix. It's not defective because it's symmetry. You remember, any symmetrical matrix is not going to be defective. Guarantee you find enough eigenvector. Since it's symmetrical, we have a repeating solution associated with the 2 eigenvectors, a single eigenvector associated with the 5. So the lambda is made by the diagonal matrix of the eigenvalues. And this is my q. The first one is the first eigenvector, second one, the second eigenvector, third is the third eigenvector. The order is very important because my order is lambda 1, lambda 2, lambda 3. Then in the eigenvector q should be v1, v2, v3. They're matched. So this match this, this match that, this match this. Keep that order. So this is the eigen decomposition, means this will equals q lambda q inverse. And the q is right here. So let's take advantage of this decomposition. How do you calculate the a to the 6th power? Well, a to the 6th power, I have the q here, made by eigenvectors. Q inverse, guaranteed, because it's non-defective. And all you need is to calculate the 6 powers of the 3 eigenvalues. If you think about a scaling operation, each time you just scale by this much, 6 times, you do 6 times. That's it. So the computation is this number, and you see there's only 2 numbers here. If you look, they're all the same number. The last example I want to show you is the polynomial. How do you calculate this polynomial I showed you for the PA? Well, the A is pretty complicated. If you do it directly, you can try, probably you won't finish it by hand. You can use MATLAB to do it. The best way is use the eigen decomposition. You write A as Q inverse, Q lambda and the Q inverse. Then the PA, all you need is look at the P of the 3 eigenvalues. The P of the 3 eigenvalues, let's do 1 at least. Inverse, -1. 4 P -1 plus 4 times plus 6 plus 4 plus 1. That's 1 minus 4 plus 6 minus 4 plus 1. What is that? 8 minus 8 is 0. So it's going to be 0 here, 0 here. And the last one, P5, is 1296. That is a very easy calculation. You just do 3 polynomials and then multiply Q inverse, then you get your result. You wanted me to show you how to use the MATLAB to do it? Well, then what you do is claim a function. You need to use the symbolic like P at x equals x to the 4th power plus 4 times x to the q, okay, and plus 6 times x squared plus 4 times x plus 1. That's the polynomial. And what next? Then you are going to call it, this is the command, P5. Then return back to this. And the P1, -1, return 0. Then you get this. So what you need to do is claim the Q equals claim the A first, equal the matrix you have. What is the matrix for the A? Oh, here you go. If we claim the A equals 1, -2, 2, -2, 1, and the 2, -2, 1, what's next? You're going to claim the eigenvector Q D or Q lambda equals eigen of A, right? That's what you needed to do. And then you got this Q and the lambda. In the end, you're going to say your P of A just equals Q multiply P of lambda multiply Q inverse. You get the result. That's it. You know, look at the result. There's only one number, 432. So by using the matrix, of course, it releases the power of computation. But all you need in this hour is to pay attention to the defective matrix. How do you know it's defective? Well, you need to understand the property of a matrix when you try to figure out the eigenvector. That's how you detect. Or you can use MATLAB to see if it's defective too. Look at the rank command. So anyway, we can talk about the tutorial of MATLAB offline. I posted some tutorial resource there if you need help. Or you can ask my help in the office hours. Thank you for today, And see you next time. It will be the most interesting application. We're going to talk about the $25 billion eigenvalue problem. Actually, this is underestimated. It's not a 25 billion. Look at the influence, could be $250 billion. Thank you, and see you next time.